Hi everyone, I'm Julia, the chemistry tutor, and today I am going to talk about the individual gas laws and combined gas law. So we've already talked about the ideal gas law in a previous video that I did. So today we're going to talk about all of the other gas laws that are not the ideal gas law, okay? Okay, so we've already talked about, excuse me, the ideal gas law, which is PV equals nRT. Okay, that's in my previous video. And one of the things I want to talk about with this is the relationship between PV and T, your pressure, your volume, and temperature. We know R is a constant, right? That value never changes. N is usually constant, right? In order to change our number of moles, we have to either add gas or remove gas. We typically don't do that, so usually N is held constant. There's one law that it's not held constant, and we'll talk about that, but usually it's held constant. So if we're looking at just pressure, volume, and temperature, okay, so if I said my pressure was 4 and my volume was 2, that's going to equal that's going to equal 8. Okay, so what if I double my my pressure, and leave my volume where it is? Well, I have to double my temperature. Okay, so pressure and temperature are what we call directly proportional because they are on opposite sides of the equal sign. Okay, so if one goes up, the other one has to go up. If one goes down, the other one goes down by the same amount, directly proportional. I doubled my pressure, I doubled my temperature, keeping my volume constant. Okay, the same thing would happen with volume. If I left my pressure at 4 and doubled my volume, again, I would have to double my temperature. So volume and temperature are also directly proportional because they are on the same side of the equal sign. Okay, so let's look at pressure and volume. So if my pressure, we'll start with where we were again, pressure 4, 2, and 8 for temperature. If I raise my pressure to 8 and want to keep my temperature constant, then that means my volume has to go down by 1, right? If I double my pressure, I half my volume. Those are inversely proportional. Pressure and volume are inversely. Ooh, I might need an E in there. Inversely proportional. Okay, because they are on the same side of the equal sign. This one up here, opposite. Okay, so those are things to keep in mind. Pressure and temperature relationship, volume, temperature relationship, volume, pressure relationship. Okay, so those are our relationships between pressure, temperature, and volume. Mathematically, we can see that our pressure and temperature, if pressure goes up, temperature goes up. Pressure goes down, temperature goes down. Same thing with volume and temperature. Pressure and volume are opposite of each other. If pressure goes up, volume goes down. If pressure goes down, volume up. Same if volume goes up, pressure down. Volume down, pressure up. Okay, inversely proportional. Okay, so the reason we're talking about those is because we have a few individual gas laws, and one, excuse me, one of them is the first pressure and the first volume. If I change that pressure, my volume is going to change. Okay, that is Boyle's law, and that is at constant temperature and constant volume and constant R and constant number of moles. We're keeping those constant all the time right now, unless I say differently. Okay, so another one of our individual gas laws is if we are looking at pressure and temperature together. Okay, and I'm not going to go into the math of where these come from. Okay, I'm not going to do all of the algebra and the math showing where these individual laws come from. Okay, if you want to know that, schedule an appointment with me at Julia Kim Tutor at Outlook. Email me and we can set up an appointment if you want to talk a little bit more about where those equations come from. I'm not going to go into that in this video. Okay, so my pressure 1 over temperature 1, my pressure 2 over temperature 2, that is Gay-Lussac's law. Okay, and that's when you're at constant volume. Okay, we have another one that is our volume compared to our temperature, and our volume, second volume compared to our second temperature. And that is Charles' law. Okay, and that is at constant pressure. Okay, and so for all of these, we are assuming constant number of moles, and R is always constant. Okay, so there is another law that takes into account your first volume and your number of moles, if you are changing your number of moles, and your second volume and your second number of moles. That is Avogadro's law. So in the previous video, I had talked about this is at constant pressure and temperature. And remember in the last video, ideal gas law, I talked about at constant temperature and pressure, we can say our moles in our balanced equation is equal to our number of liters. That has a lot to do with this law being mixed with Gay-Lussac's law. Okay, and so I'm not going to go into that. I'm not going to talk heavily about that. We just need to know this law. If we are changing our number of moles, volume is going to be related to that. Okay, and they're on opposite sides of the equals sign, right? In PV equals nRT, they're on opposite sides of the equals sign. So they are going to be inversely proportional to each other. Okay, but from combining Gay-Lussac's law and Avogadro's law and some other information in there, that's where we get this thought that at constant temperature and pressure, your number of moles is equal to your liters in your balanced equation. Okay, and then we have one more law, and that is Dalton's law of partial pressures, that says our pressure total is going to be equal to pressure of our first gas plus the pressure of our second gas plus the pressure of our third gas, on and on and on. However many gases are in there, the pressure of each individual gas adds up to the total pressure. So like if I had this tank here and I had oxygen and carbon dioxide and some hydrogen in there, each one of them is creating their own pressure in that container. And the addition of all of those pressures added together is my total pressure. That is Dalton's law of partial pressures. Okay. So those are my individual laws. I have Boyle's law, constant temperature, Gay-Lussac's law, constant volume, Charles' law, constant pressure, and Avogadro's law, constant pressure and temperature. And then your Dalton's law of partial pressures, which is add all your partials together and get your total. Okay, so then there is the combined gas law, where we are combining these three gas laws right here. Okay, so when we do a combination of those three gas laws right there, okay, we get the combined gas law, which is P1 V1 over T1 equals P2 V2 over T2. And that is your combined gas law. Okay, and this is the gas law we're going to go to most often when we're talking about any of these individual laws, any of those top three laws, Boyle's, Gay-Lussac's, and Charles' law. Because when I'm given my information, let's say I were given a pressure of 3.6 atm, a temperature of 25 degrees Celsius, a second pressure of 4.2 atm, and I'm asking about that temperature. Okay, they didn't say anything about volume. Volume was not mentioned, so you can get rid of it. And we get Gay-Lussac's law. Okay, if I said I had 27 degrees Celsius and 4.2 liters, and I had 50 degrees Celsius, and I'm asking about that other liters. Okay, so in that case, in this combined law up here, okay, they didn't mention anything about my pressure. So I could leave my pressure off, and I get Charles' law. That should be a 1, not a 2. I get Charles' law. What if I had 4.7 atm and 7.0 liters, and here I have 2.6 atm, and I'm asking you about the other liter? Well, in this case, let me get rid of all those little lines there. Okay, so in this case, I didn't say anything about my temperature. So temperature was held constant. We can get rid of it. And we get Boyle's law. Okay? So in the combined gas law, if you see two pieces of anything, two pressures, two volumes, two temperatures, you write down your combined law, cross out anything they don't mention or they say is held constant, and you get your other individual laws. Okay? So that's how we use the combined gas law to get 3 of our other individual laws from it. Okay? Okay, so let's do some problems with this information that we've been given, all those laws we've been given. So when I look at my information here, oh, hold on. Okay, I had to fix that so I could actually write on it. Okay, so looking at this problem, I've been given a volume, a pressure, drives in low valley, where atmospheric pressure, I've been given another pressure, and it's asking about my new volume. So your big thing to recognize is that you have been given 2 pressures. So you know you cannot use the PV equals nRT because that doesn't have 2 of anything in it. You cannot use the ideal gas law for that. It doesn't have 2 of anything in it. Okay, so you know because you've been given 2 pressures, you're going to go to that combined gas law. Okay, and I'll go ahead. I'm just going to do the whole thing over here. I'm going to write all of those things down just like I did with the ideal gas law. Okay. Oh, hold on. I'm going to pop back over here for a second real quick. Okay, so remember in PV equals nRT, because R was in there, and R is 0.08206 atm liters over K mole. Okay, because of these units, atm, liters, K, and mole, well, atm, liters, and mole, we had to be in atm, liters, mole, and K. So K, you always have to be in K no matter what. Because remember, if we have a negative Celsius, we would wind up with a negative volume, and that is not possible. So we always turn our temperature into K. But for these individual and the combined gas law, pressure and volume can be in any units as long as they are the same same pressures or volumes, same units in order to cancel. Okay. So pressure and volume. Pressure could be in millimeters of mercury as long as they're both in millimeters of mercury. Your volume can be in milliliters as long as they're both in milliliters. Okay. But your K, always, 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 temperature has to be in K. Okay. So let me pop back over to this other screen. Okay. So given my information here, I have my first volume. It's my V1 and my P1 because the two that go together are in the same sentence together. Because that's what is important about these, is that you have your ones together and your twos together. Okay, and they're written together. So I have 1.82 times 10 to the 7 liters. And the pressure that goes with that is 1 atm. My second pressure is 1.20 atm. They're asking me about my volume. So you see temperature was never mentioned. We can ignore it. So we can just get rid of temperature out of that equation over there. And we're doing Boyle's law. P1 V1 equals P2 V2. Okay, and I have all of my stuff over here. My pressures are in the same units, so they will cancel. So I'm going to rearrange this equation, right? We always say we move the things to the diagonal across the equal sign. Okay, if you're good at algebra, you're just rearranging this equation by algebra. If you struggle with algebra, we just say, okay, we're isolating V2. So we're going to move P2 to the bottom on the other side. We're dividing by P2. Okay, so my V2 is equal to my P1 V1 over P2. So now I just plug my information in there. My V2 is equal to my first pressure times my first volume over my second pressure. You see your ATMs cancel and you're left with liters, which is what you're looking for. And when I did that math, I got 1.51 66 times 10 to the 7 liters. And we are at 3 sig figs here, 3 sig figs here, 3 sig figs here. So we're going to go with 3 sig figs in that answer. So I'm going to call it 1.52 times 10 to the 7 liters. Okay. So we just pull our information out, go down the side, plug it all in, do our thing. Okay. So now for number 2, I've been given a volume, a pressure, another volume, and they're asking for the second pressure. Okay, so if we're looking at our combined gas law, because you've been given 2, right? Remember, if you're given 2 of anything, we're coming to this law. And you can already see they didn't mention temperature, so we can just leave temperature out. I meant to ask about a temperature on here, but I forgot. Okay, so I have my P1 V1, P2 V2. Okay. So we're ignoring that temperature because temperature was never mentioned. So my first volume is 5.6 liters in that same sentence at a pressure of that volume. It's a pressure of 1.5 atm. It's asking us, we have our second volume, 4.8 liters. And this second pressure is what we're looking for. That's our question. Okay, so we are isolating our P2. Oh, that was interesting. Let me fix that. I don't know what happened there. Oh, that went all the way to the bottom. Okay, so we are isolating our P2. So we're going to bring our V2 to the bottom on the other side. We're dividing by V2. So P2 is equal to P1 V1 over V2. So my P2 is equal to my first pressure, times my first volume divided by my second volume. My liters cancel and I'm left with ATM, which is what I'm looking for. And when I do that math, I get 1.75. We're at 2 sig figs here, 2 here, 2 here. So I'm going to go with 2 in my answer. 1.8 ATM. Okay. So they're not so bad. We just see we've been given 2 pieces of information, 2 of one thing, 2 volumes, 2 pressures, 2 temperatures. We go to our combined law, P1 V1 over T1 equals P2 V2 over T2. Leave out anything that's not mentioned or they say is held constant. And then you just rearrange your equation and do the math. Okay, so let's look at this one here. I have a volume. I have a temperature. Gets cooled. Here's my second volume. And they're asking about my temperature. So because I've been given 2 volumes, we know we're going to P1 V1 over T1, P2 V2 over T2. Okay, if you want to write all of those down over here, you can. It's V2. Okay, my first pressure was never mentioned. My first volume is 10 liters. My first temperature is 255 Celsius, so we have to add the 273 to that. Remember the 0.15 drops off. I don't know if you remember that from the last video, but if there's no decimals in your given temperature, you don't really need to worry about the 0.15 because our answer is going to be in 0 decimal places, and the 0.15 will not round the number up. Okay. So when I do that, let me see, I don't think I have my temperatures written down on here. 255 plus 273. Oh, I am totally hitting the wrong buttons here. I get 528, so that's 528 K. They never mentioned a second pressure. My second volume is 8 liters. And my second temperature is what we're looking for. So they never mentioned the pressure. We can ignore the pressure in this equation up here. And we get V1 over T1 equals V2 over T2. Okay, we are isolating for T2. Okay, so this we need to talk about. What you're isolating for is on the bottom. You want what you're isolating for to be on the top every single time. Okay, so you can rearrange this equation by algebra and do a bunch of fancy stuff with it, or the easiest way to do it, let me show you, if what you're solving for is on the bottom, if you're solving for the temperature in these individual and combined gas laws, your easiest bet is to first flip the entire equation. Okay, so we flip it from top to bottom. We get T1 over V1 equals T2 over V2, okay? And if you question that, plug some numbers in, do it, you will see they're still equal to each other. Okay, so I'm isolating my T2. So I'm going to bring my V1 to the top on the other side. Remember, it just goes to its diagonal across the equal sign, because what we're doing is we're multiplying by V2 and it cancels, so we multiply the other side by V2. So we get that T2 equals my T1 V2 over V1. Okay, so now that I have all of my numbers in the correct units, I'm in K for temperature, and my volumes are both in the same units. So my T2 is equal to my first temperature, 528 K, times my second volume, which is 8.00 liters, times, divided by my first volume. My liters cancel, and I'm left with K, which is what I'm looking for. And so when I do that math, I get 422.4, and we're limited to 3 sig figs here, 3 here, 3 here. So I'm going to go with 3 in my answer. So I get 422K. Now, what if they had said in Celsius? What if they said, what will your new temperature of the gas be in Celsius. Okay, so now remember to go from K to Celsius, we would subtract that 273. And I did not do that math, so let me do that math real quick. And I get 149C. Okay, so if they ask for it in C, you have to subtract that 273. If they don't ask for it in C, you can just leave it in K. So now calcium carbonate decomposes, so I have a temperature here. I have a volume. And, oh, there's temperature. Okay, what will the volume of this gas be? Okay, so this temperature, that's my first temperature. Okay, they're saying it decomposes, so now if it's collected at the 1200, okay, and then we cool it down to 25, okay, so we've been given two temperatures. Okay, this is just the same temperature. We're saying it reacted at this, and now if we reacted at that. Okay, so two temperatures. Okay, and when I look at this, I mean, maybe you can look and see that they never ever mentioned pressure. So I can ignore my pressure in that equation because it was not mentioned. It means it was held constant. Okay, so my V1, T1, V2, T2. And you could have written your P's over here, but after you get all your information in, you will see that those P's have no values, so we're just going to ignore them. So we get them out of the equation. So my first volume was okay, so we see how this volume was at that temperature. So my first volume is 2.50 liters. My first temperature is 1200 C, but we have to add the 273. And because this one has decimals in it, we have to use the 0.15. Okay, so if I add those, 1200 plus 273.15, I get 1473.15. We're limited to 1 decimal place, 2 decimal places, so we're limited to the 1 decimal place. Okay, the 5 is going to round that up, so I get 1473.2 K. So they're asking about that second volume, and my second temperature is the 25. Again, it has decimal in it, so I have to use the 0.15. And if I do that, I get 298.15. We're limited to 1 decimal place here, 2 decimal places there. So we're going to go with the 1 decimal place. Okay, the 5 rounds that up. So I get 298.2 K. So we have all of our information in the units that we need it. We are isolating that second volume. So our T2 is going to come up to the top on the other side. So I get that my V2 is equal to V1 over T2 times T2 over V1. T1. Sorry, I'm getting my letters all mixed up in my numbers. Okay, so if we plug all of that in, 2.50 liters times my second temperature divided by my first temperature. My K is canceled and I'm left with liters, which is what I'm looking for. And when I do that math, I get 0.50597. And I've got 3 sig figs here, 4 here, 5 here. So I'm going to go with 3 sig figs. The 9 is going to round the 5 up. So I get 0.506 liters. Okay. So we're just rearranging those equations. We're just tracking our information. And do you see how if I track my information over here, once I go to plug it into my equation, it's all right there in front of me. And the units that I need it, everything is as I need it. Whereas if you try to pull it out of your problem as you go, you'll be like, oh, wait, I need to convert that temperature. Let me go do that. I need to convert that temperature. Let me go do that. And then you get confused in the equation as you're plugging stuff in because you're trying to get everything figured out as you're plugging it in. So my suggestion is to always get all of your conversions done on the other side, on the side of your paper first, and then you're already in the units that you need, and then you just plug it all in. It's just labeled right there in front of you. Okay, so let's look at the next one. Let me erase a little something there so we can see what's going on here. So that was 0.506 liters. Okay, so now looking at number 5, if I have a gas and a piston at a pressure, so I have a pressure and I have a temperature, and I compress the gas until the pressure is this, what will the new temperature inside the piston be? So we're looking for that temperature. Okay, so we've been given 2 pressures. So P1, V1 over T1, P2, V2 over T2. I can see that volume was never mentioned. So I am going to just go ahead and get it out of my equation because I don't care about volume. It was held constant. So my P1, T1, P2, T2. My first pressure, 1.07 atm. My first temperature, 45, but I need to add that 273. I don't care about the 0.15 because there's no decimals in my original temperature, so those decimals won't make a difference. And when I do that, I get 318 K. And my second pressure is 915 millimeters of mercury. We're looking for that temperature. Okay, so you see your 2 pressures are in different units. They have to be in the same units. So you need to either convert ATM to millimeters of mercury or millimeters of mercury to ATM. We always go to ATM, so that's the one I'm going to do because that's just the easy one. We know it's dividing by the 760. Okay, and so when I do that, I get 1.2039. And this number given us here was 3 sig figs. This is an absolute number. Don't use that for sig figs. So I want 3 sig figs in my answer. So that's going to be 1.20 atm. Okay, so now I have all of my units as I need them. I am isolating for T2. Oh. So it's on the bottom. So we're going to flip the equation. Okay, T1 over P1 equals T2 over P2. We're isolating for T2, so we're going to move P1 to the top on the other side. Okay, so I get that my T2 is equal to my T1, P1 over P2. Oh, my P2 is on top, and my P1 is on the bottom. Okay, so now I can just plug all those numbers in there since I'm in the correct units and ready to go now. My first temperature, 318 K. My first pressure, 1.07 atm. My second pressure was the 1.20 atm. Okay. So just looking at this, okay, from our concept of knowing that pressure and temperature are directly proportional. They're on opposite sides of the equal sign, directly proportional. Okay, so we know that if pressure goes up, temperature goes up. If pressure goes down, temperature goes down. So our pressure went up. Here was our pressure went down. Here was our P2 and our P1. So our pressure went down, which means we should expect for our temperature to go down. So that temperature should be lower, and it is not. Wait, our pressure went, hold on. Give me a second. I have these mislabeled. So my P2 was 1.20, and this needs to be P2 on the top. So that needs to be P2. I knew something went wrong here. See, that's how you can look and be like, wait, that's going to go down. It should go up. Okay, so my P2 was the 1.20, and my P1 was the 1.07. Okay, I'm glad I made that mistake because that shows you really have to pay attention to your ones and your twos. My first pressure, my second pressure, my first temperature, my second temperature. Okay, so looking at our pressures, our pressure actually went up, right? Our pressure increased from 1.07 to 1.20, which means our temperature should also go up, right? Because they're on opposite sides of the equal sign. If pressure goes up, temperature goes up. And if I do that math, I get 356.6. And we are at three sig figs here, 3 here, and 3 here. So I'm going to go with 3 in my answer. The 6 will round that up, so I get 357 K. So our pressure went up, our temperature also went up. So that's how you can check yourself real quick, knowing those concepts that pressure and temperature are directly proportional. If pressure goes up, temperature goes up, because then you can see, like I just did, I had my pressures in the wrong place. I had them switched, and so my temperature was going down, and I knew that had to be wrong. So I knew I had something switched. So knowing those concepts that we talked about at the beginning, how pressure, temperature, and volumes are related to each other, you can do a quick check on yourself and see if maybe you switched something. Okay. All right, so let's look at number 6 here. So I've been given a volume, the gas, so it's my gas, in a metal tank. So I have a pressure, I have a temperature. If I increase the temperature, oh, that should not say balloon, that should say tank, to 39 degrees, what will the new pressure be? That should also say tank. Okay. So I see I've been given 2 temperatures. So automatically I know I'm going to P1, V1 over T1, P2, V2 over T2. And I've been given pressures, temperatures, and volumes. So I'm going to track them all over here. Okay, so my first pressure. Okay, so you see how all of those go together. That's your first set of conditions. So I have 45.0 liters, I have 2.30 ATM, and I have 25 degrees Celsius, but I need to add that 273. There's no decimals in my temperature, so I don't need to worry about the decimals on the 273. So that's going to be 298 K. Okay. And my second pressure, oh, that's what they're asking for. What will be the new pressure? And my second temperature was the 39 plus the 273 is, I should be able to do that in my head. That's 312 K. Okay, and so what you'll notice is they did not mention a second volume, which means your volume did not change. Okay, if they don't mention that it changed, it was held constant, we can ignore that volume. We don't care about volume. Okay, so we can leave the volume out of this equation. So we are isolating for P2. So we're going to move our T2 to the top on the other side. So I get that my P2 is equal to my P1, T1, T2. See, I did that again. You got to be really careful about that over my T1. So my P2 is equal to my first pressure times my first temperature divided by my, so see, I did that again, my second temperature on top and my first temperature on the bottom. Okay, and my K's cancel. I'm left with ATM. And if you do that math, for some reason I don't have this answer on my paper, I get 2.408. I've got 3 sig figs here, 3 here, 3 here. I'm going to go 3 in my answer. 8 will round that up. So I get 2.41 ATM. Okay, and if we're looking at pressure and temperature, they're directly proportional. So my temperature went up, my temperature increased, so my pressure should have increased. And it did. It went from 2.30 to 2.41. Okay, so just that quick check on ourselves. Okay, so now we're going to get a little bit more into it. Okay, so on this one, I've been given, I've been given a number of moles of a gas, been given a volume at a particular temperature. They didn't tell us what temperature, particular temperature and pressure. They didn't say what volume. There's my question, and there's my moles. Okay, so I know I've been leaving the moles out of that combined gas law. If we put moles in there, it goes on the bottom with temperature. Because on PV equals nRT, your N and your temperature on the same side, so they go in the same place on there. Okay, and if we look at this, we've been given volumes and moles. We have not been given pressures or temperatures, so we can ignore the pressures and temperatures in that equation. Okay, so if you're given moles in these, like 2 sets of moles, or moles in something that has 2 liters or 2 pressures or 2 temperatures or 2 whatever, we have to include moles into that mixed gas law, which is P1, V1, N1, T1, P2, V2, N2, T2. Remember I said we normally keep our number of moles constant? Well, in this case, we did not keep them constant. Okay, so we ignored the pressure and the temperature because they said just at a particular, it was held constant because they didn't give you any changes. So we're using the V1 over N1 equals V2 over N2. We're isolating for the second volume. So we're going to move our moles to the top on the other side. Okay, so I have my V1, N1, V2, N2. Okay, I have 3.25 moles to start with, and that is at 1 liter. And I'm looking for the second volume. My second moles is 4.15 moles. Okay, so when I plugged them all in, I had rearranged and got that V2 is equal to V1 N2 over N1. So that's equal to my first volume, or my second moles, divided by my first moles. Moles cancel and you're left with volume. And if you do that math, you get 0.022968. And we've got 3 sig figs here, 4 here, 3 here. So we're going to go 3 in our answer. So the 6 rounds the 9 up to a 10, which rounds that 2 up to a 3. So I get 0.0230 liters. Okay. So now, if I look at this next one, I have a mass of gas. So when you get a mass of gas, you're probably going to have to convert it to moles, most likely. Okay, I have a volume at a certain temperature and pressure, so those were held constant. And I have another mass, and we are looking for what volume? What is my second volume? Okay, so again, P1, V1, since moles were mentioned, we're going to put it in there. Okay, so, and they said at a certain temperature and pressure, which means those were held constant, so we can get rid of temperature and pressure. Okay, so I get the same thing again, that my V1 over N1 equals V2 over N2. Okay, so if I track those over here, get my V1, N1, V2, N2. So my first volume, 7.20 liters. My first N, I have to convert that grams of gas. And grams to moles is always molar mass. 2 oxygens weighs 32. Okay, and if I do that math, oh, I do have this on here. Okay, I get 16.0 moles because we're at 3 sig figs on that 5. Okay, my second volume is what they're looking for. And my second number of moles is, I had 15 grams of oxygen. I need to convert that to moles. Okay, so when I do that, I get 480. That cannot possibly be true. Hold on, I have something wrong here. Nope, I calculated wrong over there. So my 15 divided by 32. Oh, I did my other one wrong too. I have both of those wrong. So hold on a second here. So I get 0.46875. And this is 3 sig figs, and that's 4 there. So I'm going to go 3 sig figs. So it's going to be 0.469 moles. And this one up here, I calculated wrong. I had them in here wrong. So this is 5 divided by 32. So that one comes out to be 0.15625. And I have 3 sig figs, so 3. So I'm going to go with 0.156 moles there. Okay, so now I'm isolating, I'm solving for V2. So N2 is going to come to the top on the other side. So my V2 is equal to that V1, N1. Oh, N2, I did that again. N2 over N1. So my V2 is going to be equal to the 7.20 liters times my second moles, 0.469 moles, divided by my first moles, 0.156 moles. And since I did all of that wrong on my paper, I need to calculate that real quick. And I get 21.646 and some other numbers. And we've got 3 sig figs, 3 and 3. So I'm going to go with 3. So that is 21.6 liters because our moles canceled. We're left with liters. Okay. Okay, so we can slap moles into that combined law. Okay, so over here on this paper, I could have called this combined law an N1 and an N2 down there. Okay. All right, so let's do a couple more problems. Okay, so now I've got this gas. So I have 6.5 liters of a gas at 24 and that pressure. I've got another temperature, another volume, and they're asking, this should be pressure. That should be pressure. Okay, so I've been given 2 volumes, 2 temperatures, so I know I'm going to have to use the combined law. So P1, V1 over T1. Moles or grams of gas was never mentioned, so I'm going to leave N out. So P2, V2 over T2. And we have all of those in there, so I'm going to track them all. So my first pressure was the 812 millimeters of mercury. My first volume, 6.50 liters. My first temperature was 24 Celsius, but I have to add the 273. And since there's no decimals in my temperature given, I don't need to worry about the 0.15. So I get 297 K here. My second pressure is what we're looking for. My second volume was the 5.00 liters. And my second temperature was the 50 Celsius, but we have to add the 273. And we get 323K for that. So we're solving for P2. So we're going to isolate P2, which means my V2 moves to the bottom on the other side, and my T2 comes to the top on the other side. Because basically what I'm doing is I'm multiplying by T2 and they cancel, so I have to multiply the other side by T2. I'm dividing by V2 and they cancel, so I'm dividing the other side by V2. Okay. So we get that our P2 is equal to our P1 V1 T2 over T1 V2. And just to have this in your brain, I could have written this T2 P1 V1 is the same as P1 V1 T2. It doesn't matter what order you do multiplication in. Okay. So then on the bottom, I've got the V2 T1. Okay, so now, first of all, to recognize my temperature units are correct. My volume units are the same, because remember, R is not in here, so you do not have to be in liters. You could be in milliliters. They just have to be the same units. And my pressure can be in any units as long as they're the same. So my answer is going to be in millimeters of mercury. Okay, so my T2 is 323K. My P1 is 812 millimeters of mercury. My V1 is the 6.50 liters. My V2 is 5.00 liters. And my T1 is 297K. Okay, my K is cancel, my liters cancel, and I'm left with millimeters of mercury, which is the pressure unit I'm looking for. So now, when I do all of that math, and I don't know if I have that problem still here on my paper. Oh, I do. Okay, so let me look here real quick. Okay, nope, I do not have that math on my paper. So let me just calculate that real quick. Okay, let me just double check my numbers here. So that's my second temperature, my first pressure, my first volume, my second volume, and my first temperature. Okay, so I get 1148.009, and I've got three sig figs, 3, 3, 3, 3. So we're going to go with 3 in our answer. The 8 is going to round the 4 up. Okay, but you see 115 does not mean the same thing as 1,480. So I need to put a 0 in there to get me in the thousands place. But do not put a decimal on the end. A decimal on the end would make that 4 sig figs. Remember, ending zeros are significant if there's a decimal in the number. So that is going to be 1150 millimeters of mercury. So we don't have to hold anything constant. If we're not holding anything constant, you just put everything into the equation. Okay, let's do another quick one of those. So I've been given a volume, a temperature, and a pressure. I've been given another pressure, another temperature, and asked about the volume. Okay, so we've been given 2 temperatures, 2 pressures. No moles were mentioned, so I'm going to leave moles out. Okay, so my P1, V1, T1, P2, V2, T2. Okay, so my first pressure was the 785 torr. My first volume, 4.35 liters. My first temperature was the 30.0 Celsius, but we have to add the 273. And I'm going to use the 0.15 because there is a decimal in our given temperature. I get 303.15, and I'm to 1 decimal place here, 2 decimal places here. So I'm going to go with 1 decimal place in my answer. So the 5 is going to round the 1 up, and I get 303.2 Kelvin. My pressure, second pressure was the 1.5 atm. My second volume is what we're looking for. My second temperature was the 50. And we're going to use the 0.15 on the Celsius because we have a decimal in our given temperature. And I have a mistake there. So 50. I've got all kinds of mistakes going on that problem. So I get 323.15. And we're limited to 1 decimal place, 2 decimal places, so 1 decimal place in my answer. The 5 is going to round the 1 up, so I get 323.2 K. All right, so looking here, our pressure units are not in the same unit. They have to be in the same unit. So I could either switch my torr to ATM or my ATM to torr. Since we switched it from millimeters of mercury to ATM last time, let's switch it from ATM to millimeters of mercury this time. Okay, so I know my conversion is 760 torr. Remember, torr and millimeters of mercury are the same. 1 ATM. So if I do that, I get 1140. I'm going to keep that number. I know I'm limited to 2 sig figs there, but I'm going to keep that number for now, because I don't want to make that 1100, because that's going to throw our number off pretty heavily rounding at this point. Okay, when we round just a little tiny number at the end, like over here, well, over here where I'm rounding right here, okay, that one little tiny number at the end is not going to make a huge difference. But here, if I were rounding this number, that's a difference of 40. That's going to make a pretty huge difference. So I'm not rounding that number yet. I just need to remember that it is 2 sig figs. Okay, so it's 1140 torr, and it's 2 sig figs, those two. Okay, and I am solving for my second volume. So my P2 is going to come to the bottom and my T2 to the top. So I get that my V2 is equal to P1 V1 T2 over T1 P2. So I'm just going to slap my information in now that we're in the correct units and everything. So my first pressure, 785 torr. My first volume, 4.35 liters. My second temperature, 323.5 K. My first temperature, 303.2 K. And my second pressure, which was 1140 torr. Torrs cancel, Ks cancel, and you're left with liters, which is what you're looking for. So now if I do that math, I get 3.1959 and some other numbers. And we've got 3 sig figs here, 3 here, 3 here, 3 here. And this one was 2 sig figs. So we're going to have 2 sig figs in that answer. The 9 will round the 2 up. So I get 3.2 liters. Okay. And these aren't as easy to estimate, like, is that correct? Is that not correct? If we look, we see that our pressure went up and our temperature went up. So the volume would go down with the pressure going up, but go up with the temperature going up. So each of those causes the volume to do a different thing. So you can't really estimate, because your volume would have gone up with one and down with the other. So we're not going to do an estimation on that. Okay, so both of those where you were given enough information that you had to put everything in. Okay, so now we're going to look, actually, hold on a second. Okay, I'm actually going to come back to this problem for a second real quick here. If I had decided instead to convert that first pressure, so if my first pressure at 785 torr, if I had converted that into ATM, okay, so if I decided to go to ATM instead of torr, you would get the same answer. Okay, so I've got 785 divided by 760. I get 1.03289, so I'm going to call it 1.03 ATM. So now if we had done this calculation with those instead, my first pressure was 1.03 ATM. My volume was still the 4.35 liters. That temperature was still 323.5. This temperature is still 303.2. But now we're using that ATM, my original ATM on this second pressure. Okay, my ATMs cancel, my K's cancel, I'm left with liters. So now if I do that math, oh, did I have my volume wrong there? Oh, no, that's right, 4.3. I get 3.1869, and we're limited to the 3 sig figs, 3, 3, 3, and 2. So the 8 is going to round that up, and I get 3.2 liters, just like I got before. Okay, so it does not matter on the when we're using that combined law or those individual laws with the 1s and 2s. Pressure and volume can be in any units as long as they are the same units. And no matter what you decide to convert to get them to the same units, you're going to get the same answer. I just proved that here. Okay, but remember, temperature always has to be in K no matter what. Okay, so now looking at this, and I kind of gave it away. I'm going to cover that so you don't see what kind of law this is. So I have 3 gases, oxygen, helium, nitrogen, the partial pressures. So O2 is 35 ATM. N2 is 25 ATM. And, oh, nope, I've got these wrong. 5 ATM for N2. I read that wrong. So my 5 ATM for N2, 35 for O2, and 25 for helium. So helium is 25 ATM. And they are asking what the total pressure is. So remember, when we've been given several pressures, our pressure total is going to be equal to the pressure of the oxygen plus the pressure of the nitrogen plus the pressure of the helium. Okay, so we're just going to add all of those together. Okay, and when you add all of those together, you get 65 ATM. And since this is all addition, subtraction, we're adding those. We're going to 0 decimal places, so 0 decimal places, 65 ATM. Okay, if one of those had been given to you in millimeters of mercury, you would have had to convert it to ATM, or convert the others to millimeters of mercury, or torr. Okay, so these again, because we're adding them together, they have to be in the same pressure units. Because you would not add feet and miles, right? They have to be in the same units to add them together. Okay. All right, so let's look at this next one. We've only got a couple of problems left. Oh, so this has a lot of information in it, right? But let's not freak out. So I have a testing lab uses to collect a sample of air near a leaking natural gas line. Okay, so the total pressure in their cylinder is this. So I'm going to go ahead and write that down. Pressure total, 776.134 millimeters of mercury. It contains oxygen nitrogen, and methane. I'll tell you methane is CH4. You don't need to know the formula for it in order to do this. Okay, and they say, what is the partial pressure of methane? So it's asking for the pressure of methane. If oxygen is 0.334142 atm, and nitrogen was the 515.390 millimeters of mercury. Okay, so we know Dalton's law, right? We have several individual pressures. So we know our pressure total is going to be equal to our pressure of oxygen plus our pressure of nitrogen plus our pressure of methane. Okay, so if we want to know methane, we're going to subtract off our other two pressures. Right, so our pressure total minus the two pressures we know gives us the pressure we have left. But these all have to be in the same units. Okay, so you can either convert this ATM to millimeters of mercury or convert your millimeters of mercury to ATM. I'm going to do the ATM to millimeters of mercury because that's only one conversion. So I have 760 millimeters of mercury for every one ATM. I get 33. That's not true. I am doing all kinds of crazy calculations today. Okay, so I get 253.94792. And on that, we're limited to 6 sig figs. So 1, 2, 3, 4, 5, 6. Okay, so my 9 will round that 7 to an 8. So I have 253.948 millimeters of mercury there. Okay, so now to do this math, our pressure total, they told us, was my 776.13 millimeters of mercury. And we're going to subtract off, I'll do it like I wrote it up here. We're going to subtract our pressure of oxygen, which was 253.948 millimeters of mercury, minus my nitrogen, 515.390 millimeters of mercury. Okay, when I do that math, I get 6.792 millimeters of mercury. And that's all addition subtraction. So we are 2 decimal places here, 3 decimal places here, 3 here. And so I'm going to have 2 decimal places in my answer. So that's going to be 6.79 millimeters of mercury. Okay. You could have converted the others to ATM, and then your answer would be an ATM. It would be a very different number because ATM and millimeters of mercury are not the same thing. Okay, but you can go to either one. If your teacher doesn't specify what units they want you to be in, you could go to either pressure unit. It's totally up to you. Okay. These next 3 problems that I'm going to do, the last 3 problems, are a little bit involved. Okay, they seem like it's got a lot going on and it is a lot of calculations, but we just follow our process and it's really quite easy. Okay, so we have a container that holds 30 grams of helium, 5 grams of neon, and a 1500 ml container at that temperature. So what is the partial pressure of each gas? So we need to know, and then what is my total pressure? Okay, so we need to know if I'm looking at helium. Okay, we've been given gas law information. We're looking at them separately. Okay, so I've been given 1 pressure, 1 temperature, 1 volume. Well, 1 temperature and volume and asked about 1 pressure. So we know we're using PV equals nRT for these. Okay, so I cannot combine them both into one thing because I only have 1 of each in there. Okay, so for helium, my pressure is what I'm looking for. My volume is my 1500 mils, but that needs to be in liters. So we're going to do that right here, right now, so we don't forget. Those zeros are not significant at the end, so that only has 2 sig figs, so 2 in my answer there. My temperature is 25 degrees Celsius. So we're going to add the 273. I'm leaving off the 0.15 because there's no decimals in my temperature given. So that's 298 K. And my N for that, here, move this down. So my N and my temperature. So my temperature, we said was, oh, now I need to do all of that again. So 25 plus the 273 is 298 K. Okay, so this moles, remember when we were doing the ideal gas law and the ideal gas law problems, the number of moles, if we were given a mass of gas, we get the moles from the mass of the gas. Okay, so I want to know how many moles of helium, and I've been given 3 grams of helium. And we know to get 2 moles, we use the molar mass on the periodic table, and helium weighs 4.00 grams per mole. Okay, so when I do that math, I get 0.75, and we are at 2 sig figs there. Okay, so I can solve this gas law problem. We want to know our pressure, so we're going to move the V down to the bottom on the other side. So my pressure is equal to nRT over V. So my number of moles, so my pressure of helium, we're working on helium here. So my number of moles, 0.75 times my R, 0.08206 ATM liters over K and mole. My temperature was the 298 K. And my volume was the 1.5 liters. So you see your liters cancel, your moles cancel, your Ks cancel, and you're left with pressure, ATM, which is what you're looking for. Okay, so let me calculate that real quick. I get 12.22694, and we're at 2 sig figs here, 4 here, 3 here, and 2 here. So I'm going to go with 2 in my answer. So that is 12 ATM for helium. It's the partial pressure of helium. Now we need to do the same thing for neon. So for neon, my P, V, N, and T, my pressure is what we're looking for. My volume was the same, 1.5 liters. My temperature was the same, 298 K, right? Because they're both in the same tank at the same volume and the same pressure. I mean, the same temperature. So we're using the same temperature and volume for both. Okay, my number of moles, I want to know how many moles of neon. And they told us we had 5 grams. So my 5 grams of neon. And our molar mass on the periodic table is 20.18. Okay, so if I do that math, I get 0. Oh my goodness, I am so sorry about that. Sometimes my tablet just has a mind of its own. Okay, so 0.24777 and some other numbers. We're at 2 sig figs here and 3 here, so that's going to be 2. So it's 0.25 moles. So now I can solve this gas law. We're solving for the same thing, pressure. So again, we're still using our P equals nRT over V. So my P is equal to my moles, 25, we rounded, we decided to round there. You can not round if you want to and round at the end, it's totally up to you. So my moles, my R, my temperature, and my volume. And you see your liters cancel, your moles cancel. I lost a K somewhere along the way. Oh, there it is. My K is canceled. I'm left with ATM, pressure, which is what we're looking for. So now if I do that math, I get 4.07564 and some other numbers. And we're 2 sig figs, 4, 3, and 2. So I'm going to go 2. The 7 is going to round that 1 up. So that's 4.1 ATM for the neon. That's my partial pressure of neon. Okay. So now, in order to do our total pressure total, right, we're going to add those together, our pressure of helium plus our pressure of neon. Okay, so we take our pressure of helium, which was 12, and we add our neon, which was 4.1, and I get 16.1, and this is addition, subtraction. We've got 0 decimal places here, 1 decimal place here. We're going to go with 0 decimal places in our answer. So 16 ATM is the partial pressure. Okay? I mean, it's the total pressure, sorry. So my partial pressures of each one, helium was 12, neon was 4.1, and the total pressure together to sig figs was 16. Okay, so that problem seemed like it had a lot in it, and there was a lot to do. You had 2 gas laws you had to do because you had 2 gases, and then add those pressures up. That is a very valid problem that you could get on an exam or a quiz. Okay, so let's look at this next one. I have a 50-liter tank at this temperature and that many grams of helium, and I have 10 grams of nitrogen. What is the pressure, partial pressure of each gas in the tank and the total pressure? So I don't think I'm going to do this problem. I think I'm going to let you do this problem on your own because it's just like the problem above. You're going to do 2 different gas laws. You're going to do 1 gas law for your helium and 1 gas law for your nitrogen. Okay, and on this one up here, okay, same thing. We're going to turn our moles into grams, turn our temperatures into K, and we are there. Okay, we just do each one of those, get a total pressure for helium, a partial pressure for helium, partial pressure for nitrogen, and then to add them together to get your total pressure. Okay, so I'm going to leave that one for you to do if you want to do it. Okay, and this is our last one we're going to do. And if you're in allied health chemistry, they may or may not have you do this type of problem. If you're in general chemistry, you're definitely going to do this problem. Okay? Okay, so they've given us our moles of nitrogen, moles of oxygen, moles of carbon dioxide. I'm going to write this down here. So nitrogen, I have 4 moles. Oxygen, I have 9 moles. And carbon dioxide, I have, oxygen was the 6 moles. My nitrogen was my 9 moles. Okay. And they told us the total pressure is 986 millimeters of mercury. Here, let me abbreviate that like I've been doing it. Pressure total is 986 millimeters of mercury. Okay. So the one above gave us like temperatures and volumes that we could do a gas law with, a PV equals nRT. I don't have enough information here to do PV equals nRT. I don't know my temperature. I don't know my volume. All I know is my pressure and my number of moles. Okay, so when we're doing this, this is what we use. We call the mole fraction. Okay, we look at what fraction of that pressure is nitrogen giving? What fraction of that total pressure is oxygen giving? What fraction of that pressure is the carbon dioxide giving? Okay, and to get your mole fraction, you just divide your moles by your total number of moles. My total number of moles here is, what do I have there? 19 moles. So I have 19 moles total. Okay, so my nitrogen is 4 moles over 19 moles times my total pressure. My oxygen is my 6 moles over my 19 moles times my total pressure. And my carbon dioxide is 9 moles over 19 moles times my total pressure. Okay, it's the fraction that of the total moles, what fraction of those total moles is it adding to that total pressure? Okay, so if I do that first one, I get, oh, that's not right. So 4 divided by 19 times 986. So I get, that guy is 207.5789. And these are absolute numbers. Your moles are absolute numbers. So we're going to use that for sig figs. So we're going to have 3 sig figs. 5 is going to round that up. So 208 millimeters of mercury from your nitrogen. 6 divided by 19 times my 986 gives me, oh, it gives me a very small number. Hold on. Oh, I divided by my 986. No wonder something seemed wrong there. Times 986. Okay, so this one I get 311.3684 and some numbers. So again, we're 3 sig figs. So that's 311 millimeters of mercury. And then this one, 9 divided by 19 times 986, I get 467.052, 3 sig figs, 467 millimeters of mercury. That's their partial pressures. Now, if we wanted to double check ourselves, all of those pressures should add up to my total pressure. So 208 plus 311 plus 467 gives me 986 millimeters of mercury total. Okay. So if you are given just how many moles of each gas you have and a total pressure, you're always using the concept of mole fractions for that. Your moles that you have divided by total times your total pressure, and then add all of those together. Okay. So yeah, that is all of the problems that I have. Okay. So remember, we've got a variety of individual gas laws. Okay, you may need to remember these laws. The way I remember these laws, I know it sounds weird, but at constant temperature, Boyle's seems like it would have temperature in it, but Boyle's is the one that's at constant temperature, so you leave the temperature out. I always remembered Gay-Lussac's because the thing that we use for this as a demonstration is this thing that looks kind of like a toilet float that has a pressure gauge here. And you dip this into either hot or cold, and it's a constant volume. And I always remembered, I know this sounds crazy, but I always remembered that, oh, it's that gay-looking toilet float thing. It's Gay-Lussac's law, that stupid gay-looking toilet thing, okay? And sorry if I offend you by saying that. I don't mean to offend anybody with that, but that's just how I always remembered it. Okay, and then by default, I know my last law is Charles' law. Okay, and then Avogadro's law, Avogadro, remember Avogadro's all about the how many things do we have in one mole? So Avogadro's all about the moles. So Avogadro's law is the one that has the moles in it. Okay, so those are, and then Dalton's law of partial pressures. You know, if it says partial pressures, it's going to be a bunch of those added together to get your total. And if you use your combined law, when you see 2 pressures, 2 volumes, 2 temperatures, and then just cross out what they don't mention or they say is held constant, then you get your individual law that you need. And I do believe that is all I have to say about the mixed and combined gas laws. So now I have done everything with gas laws. I have the one video on the ideal gas law, and then this video on the combined and individual laws. And I think I've done everything we're going to do with gas laws. And remember, if you ever want any extra help, you're always welcome to email me at juliakimtutor@outlook.com and schedule an appointment. So have a great day.